Welcome back again. So let us begin with this example 3.8, which is addressing the condition of, say, don't care condition. So we already know how to simplify a Boolean expression. Say here sum of product form is given, that is the summation 1, 3, 7, 11, 15. From here we come to know this requires 4 variable Karnaugh map. 4 variable Karnaugh map is essential from there. But here one more condition has been given, that is called don't care conditions. These conditions are not specified whether is uncertain. It may be 0, it may be 1. That is why it is called don't care condition. But while simplifying this Boolean function with the help of Karnaugh map, we may assume it either 1 or 0 based on the probability of making it either group of ones in the form of pair, quad or octet, okay, or even group of 16 ones if it is possible. So let us see with example we come to know here 1, 3, 7, 11, 15. So let us see 1, 3, 7, 11 and 15. These are the midterms. Okay. What should I write? Summation. And function is given it. Function is a f is a function of w, x, y, z. And d don't care w, x, y, z is equal to summation 0 to 5. At 0 to 5 we don't care, and however at 1, 3, 7, 11, 15 the function is logic 1. So don't care condition is, what is this conditions? 0 to 5. 0 to 5. Okay, so we make a Karnaugh map, K map, which is here. So wx on this side here, and yz at this side. Okay, so wx you can write here, although they are writing with 0, 0, 0, 1, 1, 1, 1, 0, you can write alternatively like this. W bar x bar, W bar x, Wx and Wx bar. Okay. So I used to write like that instead of 0, 0, 0, 1, 1, 1, 1, 0. I mean, you can see there is one bit change with respect to its adjacent value. So that is called a Greek code order. Similarly, this side y and fill up the information. So you can see at 1, this is here M1, we put here logic 1. At 3, this is 3, 1, 7, 1, 11, this is 11, 1, and 15, 1. So this red colors is the entry for f is equal to summation 1, 3, 7, 11, 15. And now we want to put the entries for don't care. For don't care, d is 0 to 5. So let me take another color here. Suppose I take this color. So this is 0 here. I put here don't care condition as x. This x can take the value either 0 or 1 based on the situation. Then 2, where is M2? This is M2 and we put here don't care. Then 5, this is 5 and 5, this midterm number 5, so here x. And at the rest places the function is 0. So that is why you can see here this is 0 written. I will take another pen. This is 0 here, then 0 here, 0, 0, 0, 0, 0, and 0. So this is how we have inserted the information as given as per the function. That is a function of w, x, y, z in the Karnaugh map. This is the step number 1. In the step number 2, we have to solve it. So Let us see how can we solve. So if we look, of course, we have to give priority to these confirmed numbers like 1. So here we can say, let me use this red, okay. So this one, M3, M7, M15, and M11. If you consider, they are making group of 4 adjacent ones. So that is becomes a quad. So we can consider this is as one of the solution. Okay. Now if that this one is remaining, okay. In order to cover this one, in order to cover this one, we have different options. So we can make group of 4 ones if we consider M0 don't care condition as 1 and M2 don't care condition as 1. This 0 and 2 is don't care condition if we assume as 1, then what will happen? Then this will be group of 4 ones in order to make this one. Okay. So this is what is written here. This may be one of the solution. So from here, first one which is given in the red color, this one I am tracing it with yellow color. This one, what we are getting the solution? We are getting the solution as one that is the yz. So yz is written here, f is equal to yz. And the second solution which is shown here is coming from this. So that solution is 0, 0 with respect to this wx. So this is nothing but w bar x bar. So that is why the solution is w bar x bar. This is one solution. What will be the another solution? Another kind of solution. That is why we used to tell that Karnaugh map does not give unique solution. Okay. So this is one solution which is correct. Another solution may be, here you can see in figure B, 3.15b. First one is okay. First one is the same because this is determined value. This is fixed value. It is not uncertain value. This one here. This. So these 4 ones are making group of 4 ones, that is called quad, and solution is yz. But in order to cover this one, that is the M1, we have another alternative. If we consider don't care M5 as logic 1, then we are able to make group of 4 ones in this way. Okay, can you see? M1, M3, M5 and M7 can make a group of 4 ones, and solution will be, if we see this this axis, these 2 rows, from here what is the common? Common is from here what is the solution? Solution is
W bar Z.
yeah, from here which one is the common? From this one, from this. Yeah, that I want to know. So this is the W bar, and from this side, which
Z.
is the common? Z. This is the Z. So that is why Z. So here W bar, and from here Z. So W bar Z is the solution of this quad. Okay. So this is another kind of solution. This is also correct. This is also correct. But in this exercise, what we are trying to understand that these don't cares M0, M2, and M5, we can consider. Okay. Why we are considering? We are not considering unnecessary. Please understand. We have to take care that a redundant group should not be there. Okay. Just to make for the sake of making group of 4 one, group of 4 ones in different form like pair, quad, we are just making. Okay. No, we have to our ultimate aim is to minimize the number of literals so that whenever we are implementing with the help of hardware, lesser number of hardware circuits should be taken. So we need not to make it blindly. We need not to make group of ones blindly. We have to take. We should avoid redundant group. Redundant. Okay. Okay. Now this was about don't care. Some of the examples are also given. You can attempt it at the end of each chapter. Examples are given. Sorry, problems are given. You can attempt to understand more about this don't care condition. Now moving to today's new content, that is chapter 4. In last class we began chapter 4 and we understood about the analysis of combination logic circuit and design of combination logic circuit. These are the two approaches of designing combination logic circuit. One is the analysis. In the analysis, we basically analyze. We have been given a circuit. Find out what the circuit is actually doing. Okay, this is the analysis procedure. Can you see 4.3 section? Yeah.
Yes, sir.
So this is the analysis procedure. And steps are given like here. We have to label all gates output that are a function of input variable with arbitrary symbols, but with meaningful names. It should not be useless name. And there should be consistency. Determine the Boolean function for each gate output, then label the gates that are the function of the input variable and previously labeled gates. So please read this all four. This has been dealt in previous class. And now another part is called design procedure. In that we have been given a statement of the problem. And then we have to decide how many inputs are there, how many outputs are there, find out the relationship between input and output, and then simplify the Boolean function and realize the circuit. So as an example, we design BCD to XS3 code converter. So once we know what code converter, we can design any kind of code converter. Okay, and this was the output. Now coming to next section, that is called binary adder subtractor. Before beginning this, any question? Anyone wants to ask? You can write in chat box also. Ceiling क्या है भाई? What is ceiling? You wrote the ceiling.
सर वो दामिनी ने अपना कैमरा ऊपर के रखा था इसलिए उसका सीलिंग दिख रहा था सर.
Okay, I thought some question is there. So if no question is there, so we can further proceed. As an example of combination logic circuit, there is one important circuit is called adder subtractor. So basically adder is different circuit, subtractor is also different circuit, but in digital logic we can realize both functions, this addition as well as subtraction in the same circuit. Okay, we will see how, but let us begin. And these are the arithmetic adder, like 0 plus 0 will be 0, 0 plus 1 will be 1, 1 plus 1 will be 1, and 1 plus 0 will be 1, and 1 plus 1 will be 2. This is the algebraic addition. Earlier, if we go by logic, in logic 1 plus logic 1 will be 1 only. Is it? We have seen now. So please don't be confused. That sometimes I'm telling 1 plus 1 is equal to 1, and sometimes I'm telling that 1 plus 1 is equal to 1, 2. Okay? Logic, if we go for logic manipulation, so 1 plus 1 is equal to 1 only, and if go for algebraic manipulation, then 1 plus 1 is equal to 2. That is 1, 1, 0. Is it clear? Yes. Okay. So half adder. Half adder is a combination circuit which add 2-bit number. Okay, 2-bit number. So this is a table. 2-bit means X and Y. This is the 2-bit number. X, Y. With the help of 2-bit number, there are possibilities of making 4 combinations. What are those? 0, 0, 0, 1, 1, 0, 1, 1. In this, in the half adder, if 2-bit input is there, then what are the outputs? So there are outputs. Two outputs. And what are the two outputs? One is called sum and another one is called carry. So please, we have seen that people are writing sum first, then carry, which is not a proper order. So please think that S should be this side, right hand side, and carry should be at left hand side. Since we are dealing here logically and we are separately implementing the circuit, so while implementation it doesn't have problem, but logically or convolutionally it has a, this it has a wrong connotation. So please mind it that whenever we are writing, I will give example here x y, and what people are writing 0 0 0 1 1 0. Why it is behaving like this? Why is writing that? 0 1 1 0 and 1 1. So what is the output people are writing here? Sum and then carry. Because sum comes first, so 0 plus 0 will be sum will be 0, carry will be 0. 0 plus 1, sum will be 1, carry will be 0. 1 plus 0, sum will be 1, carry will be 0. 1 plus 1 will be 2, 2 will be carry 1, sum 0. Logic wise it is okay, but convention wise it is not, because we always write sum this side and carry this side. Isn't it? Whenever we add the number, we add here, then carry goes this side. We add the number, then carry goes this side. I think this is the convention. So same convention we should follow here, which is given in the book. So avoid writing like this. Write like this, okay, the way it is given in. But some of the book are people are following like that. Anyway, so now this answer will be same, okay. So carry is like this 0 0 0 1 and sum is 0 1 1 0. So now write the expression of sum. So here, since this problem is very easy, so we can directly write here x bar y plus this is what x y bar. Is it okay? Or we can and carry is carry is x y r. Okay, I'm writing straightforward. No, carry dot carry is x y. Is my dead slow? Let me off the camera, my camera. You can also off. Because this pen is not responding, no? I think it is taking large bandwidth. So, yeah. Carry is what? Carry is 1. And this expression is x, y. Is it okay? And sum is here and here. For this, we have x bar y. And for this, we have x y bar. So this is the solution. Another alternative way of writing, because this may not be simplified one, for this particular case it is okay. However, traditionally we go for k-bar. We use k-bar for simplifying. So here we write x bar, x, y bar, y, and we can see, let me remove first this one. This is position F0, F1, F2, and 3. So this sum is 1 at F1 and F2. So F1 and F2. This is F0, 1, 2, 3. F1 and F2. Logic 1. This is the sum. So for that, since there is no probability of making any pair, so it will be like that only. You have to write the expression whole as a whole. So this is nothing but x bar y plus for this x y bar, and for carry, same way, carry is giving logic 1 at M3. So M3 is here, make this one, and carry is equal to x, y. So using corner map also, we can write. For this particular case, this problem is very simple, so we are writing straightforward. Even corner map does not give further any simplification. So once we understand what is the expression of sum and carry, then we simply realize the circuit. Now we can realize the circuit like this here, figure 4.5a. So sum, this is sum, is summation of what? Summation of this x, y bar, and here x bar, y. So you see here x, y bar is coming from here. So this is x and this is y bar. And here x bar, y, and we use OR gate. So this is AND gate, another AND gate, and this is OR gate, we get sum. And here carry is just x, y. So this is how we can make the circuit using traditional AND OR logic. This is called AND OR logic. Here the expression of sum can be implemented with the help of a one or XOR gate. So XOR gate is nothing but, output of XOR gate is nothing but x exclusive OR of y, or x y bar plus x bar y. Okay, and carry just AND of x y. So this is another way of representing or realizing half adder. This is half adder. Okay, implementation of half adder. Sometimes we can ask implement this circuit with the help of NAND gate. At A and gates only. Okay, so NAND gates only, that to minimum number of NAND gate. So we should follow this one. Make an exclusive OR gate with the help of NAND gate. So 4 NAND gates and 2 NAND gates are required for this, for implementing AND gate. Okay, so 4 plus 2, 6. However, if you go here, it may take more gates. So let us see further. Okay, so I want to add here that sometimes we ask implement this half adder with the help of NAND gate only. So please keep into mind that how to realize. Now moving to full adder. So in the half adder, 2-bit inputs were added. In full adder, we use 3 bits. Okay, 3 bit. 3 bits. So this is the truth table. Can you see the truth table? Please respond anyone. Truth table of full adder.
Yes, sir.
Yeah, thank you. So this side is the input and this side is the output. So input is 3 variable x, y, z. Sometimes people write A, B, and C in. Third one is the carry input. And here output as usual sum and carry. S stand for sum and C stand for carry. So 3 input and 2 outputs. If 3 inputs, so 2 to power 3 is equal to 8. So there are total 8 combinations with input. So 0, you can write here 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now find out these bits for sum and carry. So 0 plus 0 plus 0 will be 0 sum, 0 carry, 0 plus 0 will be 0, and 0 plus 1 will be 1 sum and 0 carry. Then 0 plus 1 will be again same thing. 0 plus 1 will be 1, and 1 plus 1 will be 2. And how we write 2? Like this. In the binary, it means sum is equal to 0 and carry is equal to 1. And this is what is written here, 1, 0. This will be, sum will be 1, carry will be 0. For the case of 1, 0, 0. For 1, 0, 1, again 2. And for 1, 1, 0, 2. For 1, 1, 1. 1, 1, 1 is 3 because 1 plus 1 is equal to 2. 2 plus 1 is equal to 3. And how we write 3? In binary, 1, 1. This one is sum and this one is the carry. Very simple, I think. Now we have to simplify this sum. We have to write the expression of sum and we have to write the expression of carry. Let us see how it is written. So there we can use the Karnaugh map. So 3 variable Karnaugh map. So on this side we have x and this side we have y, z. So x bar x, y bar z bar, y bar z, y z, y z bar. Okay, this is how it is written here. And M0, M1, M2, M3, M4, M5, M6, M7, these are the literal places. And after that, we know where S is equal to 1. So we can see S is 1 at what places. From the truth table, we can see, let's see, M1, 2, 4, 7. These 4 places, S is equal to 1. So what are those? 1, 2, 4, 7. At these places, sum is equal to 1. And carry, similarly carry is 3, 5, 6, 7. So 3, 5, 6, 7. Okay, this is from truth table. Now we want to simplify it. So we have written here for sum, this is sum. So 1, 2, 4, 7. And we see here, there's no possibility of making any pair, group of 2 adjacent ones or 4 ones, something like that. All are in isolation. We have to write simple, okay, simply like this. For this you can see x bar, y bar, z, and for this x bar, y, z bar, x bar, y, z bar, and for this x, y bar, z bar, and for this x, y, z. Okay, so there is no further simplification. So we write exactly like that. However, for carry, let us see. Carry is 3, 5, 6, 7. So 3, 5, 6, 7. And we can see here there is a possibility of minimizing because many ones are in the pair. So we make one pair here, we make one pair here. So this one is left upper one, so we can make one pair here also. So 3 pairs. So now write the answers. So this one x, y, M5 and M7 is making what? This is x and z, x, z. M1 and M5 and M7 are making XZ, this one. Now I will look at this one. So M6 and M7. M6 and 7, this is X is common and Y is there. Y is common. XY. So first one is this one. And this vertical one, this is YZ. So YZ. So I hope you are able to understand how we have written of each pair. So C is equal to this, and sum is equal to this. Now term has come to realize. So in the book it is written that, but how I used to do like this. I will show you. Please see here. I used to take here X line like this and put a dot gate and get here X bar. Then input line Y. This is basically voltage source and Y bar. And then third one Z and Z bar. Okay. Now I want to realize the circuit. So which circuit I should implement? Although both are necessary, see, they have implemented separate. However, it should not be separate because adder is one circuit only. Okay, it is one circuit. Here X, Y, Z input and sum and carry as a output. Okay, full adder. So X, Y, Z. So this is one circuit. So cannot be implemented separate like the way here it is given. So let us see how one can implement. So for this sum, first one is the X bar, Y bar, Z. So I will take line from here, X bar, Y bar and Z. And then put and get here. Okay. Second one, X bar, Y, Z bar. X bar, Y and Z bar. Z bar from here. Then put another and get. And then third one, X. I took X, then Y bar, Z bar. This is Y bar and this is Z bar. And put another AND gate. And the last one X, Y, Z. So this is X, this is Y, and this is Z. And after that I put AND gate. After that I am combining to OR into one OR gate. Sorry. Okay, and got the sum. Similarly, I can implement here below carry one. So this will be only one circuit. Are you getting? So this way of representing or implementing circuit is easier instead of going here like this. Okay? Are you getting, class?
Yes, sir.
Yes, sir.
So whenever you are going to attempt question, please follow this method, which is convenient and easier to check as well also. Okay. Similarly, you can implement the carry also. Will it be okay to implement carry? Just you have to extend this line
Yes, sir.
and implement carry. So this is the expression of basically sum, which is written here, is nothing but exclusive OR of Z X Y, or I can write like this: exclusive OR of X Y and then Z. Okay, and it has been expanded with the help of your Boolean postulates. So this is the carry. Okay, all expressions are given, all literals are given. And now with the help of this, yeah, you can see this is sum. Summation is what? Summation is exclusive OR of X, Y, and then Z, all three. You can see X, Y, Z. These are the inputs, this side. These are the input and these are the two outputs. One is sum and another one is the carry. Okay. Now sum is exclusive OR of X, Y. Let us see and then Z. So xy, exclusive OR of xy we can implement with the help of this XOR gate. Okay, and then exclusive OR of xy becomes the input of another XOR gate, which is giving the output of exclusive OR of x, y, and z. This is all three. So we can get z is here, that is the third input, and x, y is the here. So in this way we are able to implement sum. Now as far as carry is concerned, carry is, what carry is here? This is half adder carry. This becomes one of the input of this OR gate. And another carry is this one. How we can realize whether this one is okay or not? We can look here. Here, output carry C is equal to Z multiplied by exclusive OR of XY. Yeah, it is exclusive OR of XY plus XY. So this expression has been implemented here lastly. So you will find, if you simplify further, you will get summation is equal to 3567. 3567. Okay, this one. So, in nutshell, in brief, what is this basically? Or in conclusion wise, it is telling that we have implemented full adder with the help of two half adders and an OR gate. Two half adder and one OR gate. So this is again an interesting issue, that if we have two half adders and one OR gate, we can implement full adder. So with the same circuit, a module wise, particularly in the IC, sometimes if we have four half adders. So with the help of these two half adders and take one external OR gate, we can realize full adder. And here also another full adder. So in single IC, suppose four half adders are there. So we are able to implement or realize two full adders. So that is why module kind of implementation becomes helpful. So in this way we can have more flexibility of realizing half adder as well as full adder. Okay, got?
Yes, sir. Yes, sir.
Thank you.
Yes, sir.
So that is also one of the interesting issue. Now we are further moving towards complex issue. Suppose two numbers are there. One is a okay, right? Subscript I. Yeah, two numbers are there. One number is called output and another one number is called added. Suppose we used to write the m plus n. So this output is called suppose n, and this added is suppose n. We want to add these two numbers. So we write here as an example, m is equal to here, m is equal to here 1 0 1 1, 1 0 1 1, and m is equal to added 0 0 1 1. We want to add 0 0 1 1. This is the question. We want to add these two numbers. Okay. So what is the detailed procedure? What are the detailed things which is that is given in this table? Okay. So above is carries. This one you can say carries. So what we do? 1 plus 1 will be what? 2, and in 2 sum will be here and carry will be here. So that is why you can see one more row is given here, that is called input carry. Okay, CI. And here M is AI and N is BI. So that is why you can see there is upper number. So now you can see here 1 plus 1 plus 1. This will be 3. It means 1 will be sum and one more carry has come, which is given here. Initially it is 0 here because there is no such input carry. Now, okay, we have moved here. So now what we are doing? 1 plus this 1 as carry, which is coming from previous one. Then 0 plus 0, 1 plus 0 plus 0 will be 1, so carry will be 0, and here it will be 1. So you can see this is written here, and answer is coming what? Sum is carry, sum is coming here, and what about carry? Carry as an output. So for this case, carry was 1. Carry was 1, and here also 1. Okay, this becomes little bit confusing. Let me see. Initial carry is 0, but if we add, then 1 carry will be coming here. That is okay. And after that, this carry is here. So 1 plus 1 plus 1 will be 3. So this is 1, and 1 carry will go here. That is why this carry. And after that, we add this. 1 plus 0 will be 1, and there will be no carry. That is why C0. And if there is no carry, then this will be get 0. So that is why you can see 2 zeros are here, and we are also getting 2 zeros in this first one, and above this one. Our two numbers are there, AI and PI. We add like this. I hope you are able to understand this table, each content. Things are very simple, but we have just, you want to label it. What is the input carry, what is the output carry, what is the output, what is the added, and what is the sum. Is it okay?
Yes, sir.
This is what we used to do normally. Only we want to formalize it, we want to give the particular dates so that we can realize the circuit. It is not just simply doing the task of addition of these two numbers 1, 0, 1, 1 and 0, 0, 1, 1. We can do, we are keep doing. But now question is how to realize the circuit. Then only we have to label each and every thing. And how we can do? Here is the implementation. 4-bit adder. Now we have two numbers. That is, one is called AI, another one is called BI. I stand for here, how many bits? I is equal to subscript, that is 0, 1, 2, 3. Okay, so that is why 4-bit here, I is equal to 3 bits. Start from 0, AI 0, A1, A2, A3. Okay, that is why it is 4-bit. Now another number is B, B0, B1, B2, B3. So these 4-bit, two numbers are 4-bit, and we want to add. So this is how we can draw a logical diagram, block diagram. And this is the input carry C0. And inside this is now here full ladder. What is this inside this box? Inside this box we have this circuit 4.8. Is it okay? In the box, this is the circuit. Okay? This is full ladder. So full ladder is here. Output, input and output are given. This is the input, and this is also input. So 3 inputs are there. In the A full adder, we have 3 inputs. Yes or no? And 2 outputs.
Sir.
What is this output and another what is this output? Yes, please. Ask the question. Bolo bhai. ये सर हामी वाला था या क्वेश्चन वाला था? I do not know.
सर हामी वाला.
Okay, okay. Thank you. Okay, so we know that in full adder we have 3 inputs. These 3 inputs are A0, B0 and C0 for first case or B case. Rest will be only just labeling. And 2 outputs, sum and carry. So these 3 are the inputs. These 3 are the inputs. And these 2 are the outputs. Similarly, for this full adder, these 3 are the inputs and these 2 are the outputs. Similarly, for another, this one, these 3 are the input and these 2 are the outputs, and so on. This is the input and these are the output. I think this what is called block diagram of full adder you could understand as far as drawing what is called drawing is concerned, block diagram is concerned. Now let us do how it is working. Take it. You can take example also. Okay. You will take the same example. What was the number? Number is 1011. Uh-huh. One zero one one. And another one 0011. So here A3 is 1, A2 is 0, A1 is 1, and this is also 1. And B3 is 0, B2 is 0, B1 is 1, and B0 is 1. Is it okay? Now we will and C is here. Of course, this is, there should be no carry in advance. So what, this 1 plus 1, sum will be 1 plus 1 will be 2, now. So sum will be 0, carry will be 1. Okay, and after that here 1 plus 1 plus 1. So it will sum will be 1, carry will be 1. Okay, and then here 1 plus 0 plus 0 will be 1 sum and carry will be 0. 0 plus 1, sum will be 1 and carry will be, okay, no, 0 plus 1 plus 0, all three. So sum will be 1 and carry will be 0. So this is the answer. 0, 1, okay, this is overflow basically. So because we have 4 bits, yes. So 4 bit answer is that 1, 1, 1, 0. So we can see here also, this is 0, this is 1, this 1, and here 1, here 1. So 1, 1, 1, 0. So 1, 1, 1, 0. But here C4 is also 0. That is output of this. Okay, this is creating a problem here because in paper we have a space. We can write here C4. But in hardware there is no such things. We have to be careful. Okay. I hope you could understand this block diagram also. Okay. For today's class, I think time is over. We can conclude. Any question? Next class, we can start from carry forward. Okay, this needs background, little bit more background. So just scanning again. If you have any query, you can ask from any place. If no query, then you can sign off. Any query? Class?
No, sir.
No, sir.
Okay, then I've stopped the recording.